Hello again. This is Math 2115 coming to you from the College of DuPage, and the title of this lecture is Number Theory Continued, Prime and Composite Numbers. As always, please be an active listener as you watch this video. By way of introduction, previously we talked about the divisibility of integers, but one important concept based on divisibility is that of a prime number. We're going to see that a prime number is an integer greater than 1 that is divisible by no positive integer other than 1 in itself. This is a study that's gone on for a long time, and there have been many great theorems, including there's an infinite number of primes, and that the distribution of primes gets scarcer and scarcer as you get larger and larger. And so there's a lot of good theory there. There are also many questions that still exist about primes that are unsettled today, and they become very important in modern cryptographic systems. And so we'll talk about some of those properties that we will refer to later when we do talk about encryption, and that is our goal in this last segment of the course. So a prime is an integer p greater than 1 if the only positive factors of p are 1 and p itself, and it's greater than 1, so 1 is not a prime. A positive integer that is greater than 1 and not prime is called composite. And a number is composite if and only if there exists an integer a such that a divides into n evenly and a is between 1 and n. So as examples, the integer 7 is prime because the only positive factors are 1 and 7, whereas 9, which is 3 times 3, is composite because it's divisible by 3. Now we'll see that primes are actually the building blocks of positive integers, sort of the DNA of positive integers, as this fundamental theorem of arithmetic shows us. And the fundamental of arithmetic, which we will not prove here, states that every integer greater than 1 can be uniquely written as a prime, or as the product of two or more primes, where the prime factors are written in order of non-decreasing size. And certainly these can be powers of prime. So let's look at some examples. So here are 1, 2, 3, 4 integers, none of which are, one of them is prime actually. 641 is prime, but the others are not. So we can write them uniquely as the positive, as powers of prime. So this is 2 times 2 times 5 times 5, or 2 squared times 5 squared. So it's 4 times 25 is 100. But this is the fundamental, almost molecular or nuclear decomposition. 999 is 3 times 3 times 3 times 37. That's 3 cubed times 37. And 1024 is 2 raised to the 10th power. Now, here's an early result that was proven many years ago. But if n is a compositive integer, then n has a prime divisor less than or equal to the square root of n. Now, what that means is you only have to look up to the square root of n to try to find a divisor. And if you don't find one, looking up to the square root of n, that means it's a prime number. And so you can do a square, this allows you to reduce this, and you can do a brute force trial and error up to the square root of n. But let's look at the proof of this. So if n is composite, then by the definition of composite number, we know it has a factor a. Hence, by the definition of a factor, we have that n is equal to ab, and b is a positive number greater than 1. Now we're going to show that a is less than or equal to the square root of n, or b is less than or equal to the square root of n. If a is greater than the square root of n and b is greater than the square root of n, then ab would be greater than n times n, or square root of n times square root of n, or n, and that's a contradiction. Consequently, we see that a is less than or equal to n, or b is less than or equal to n. Because both are divisors of n, we see that n has a positive divisor not exceeding the square root of n. The divisor is either prime or, by the fundamental theorem of arithmetic, has a prime divisor less than itself. In either case, n has a prime divisor less than or equal to the square root of n, an important work. and a good application. Okay, so from that theorem it follows that an integer is prime if it is not divisible by any prime less than or equal to the square root. So this is a brute force algorithm called trial division. So let's use trial division to show that 101 is prime. Well, the square root of 101 is just a little better than 10, and so the only numbers that are under that are 2, 3, 5, and 7. And we can check all of those. It's not divisible by any of those. And so it follows that 101 is prime. Okay, so this tells us how we can check this to find primes, or to test whether something is prime. Let's look at the next example. Let's find the prime factorization of 7007. Well, if we start looking at this, you can see that 7 is does divide into that, so what we get is that this is 1001 times 7. But now we just look at 1001, and we'll check dividing this by primes, and we can begin with 7. Now we see that 7 also divides into this, so we'll have that this is going to be 7 times 7 times 143, and 143 is 11 times 13. All of these are prime, and consequently that is the prime factorization of it. You should be able to do prime factorizations, and you should think about how to write a computer program that would do this. One of the early people who studied this was in fact the librarian at the Library of Alexandria, and his name was Aristophanes, and they talked about and he wrote about a thing called a Sieve of Aristophanes. So he had a way to find all primes not exceeding a specific positive integer. And so we'll talk about how you do the Sieve of Aristophanes. And we've written it here, but let's just look at a table. So what we're going to do is we're going to write the numbers, say 1 to 100, but we'll start with 2. Now 2 is a prime, but every multiple of 2 is not going to be. So we get to delete these numbers, and we're showing that they're deleted. These are the even numbers by crossing them out. You see you've crossed out a lot of the numbers, almost half of the numbers you've done. Now we move to 3, and we get to cross out all the numbers that are now divisible by 3 with this. So now we're crossing out not just the first ones that we did, which now are double underscored, but we're crossing out new things like 9 and 27 and so on and so forth. So you see we've crossed out quite a few. Then we go to the next prime, which is 5. We cross out all the multiples of 5 and everything that was before it. And finally we go to 7, and we can check this. Now since we went up to 100, we only have to go up to 10, and the last prime that we have that is less than 10 is 7, so we're really finished here. And so you see when we've crossed out all the multiples of 7, the thing that remains are the primes that are less than or equal to 100. This is called the Sieve of Aristophanes. Here's another very important theorem, and we're going to use the proof that Euclid gave. There are infinitely many primes. And this is going to be a proof by contradiction. So we will prove this by contradiction, and we're going to assume that there are finitely many primes. So they are listed here, P1, P2, Pn. And we let Q equal P1, P2 multiplied all the way up through Pn plus 1. Now by the fundamental theorem of arithmetic, this is prime, or else it can be written as the product of 2 or more primes. However, none of these primes divides Q, because every time we try that, we get a remainder of 1. So we have that. Hence, there is a prime not in the list. This prime is either Q, if Q is prime, or it's a prime factor of Q. But this is a contradiction because we assume we have listed all the primes already. Consequently, there are an infinite number of primes. Think about this proof by contradiction. It is really quite elegant. And note that we don't state that Q is prime. And note also that the proof was non-constructive. We don't tell you how to find this, we just prove that there are an infinite number of primes, because having a finite number leads us to a contradiction. Now, because there are infinitely many primes, there are primes greater than any integer. And there's been a quest to discover larger and larger primes. For almost the last 300 years, the largest prime known has been an integer of the special form of 2 to the p, where p is prime, minus 1, 2 to the p minus 1. Note that 2 to the n minus 1 cannot be prime when n is not prime. And you might want to think about how you might prove that. Such primes are called Mercene primes. They're named after a monk back in the 16th century. And he studied them a lot, and he also was a collection point for a lot of great mathematicians. They came and talked to him. The reason that the largest known prime usually has been a Mercene prime is that there is an extremely efficient test known as the Lucas-Lehmer test for determining whether this is prime. Furthermore, it is not currently possible to test a number not of this or some other special form anywhere nearly as quickly to determine that they are prime. Testing for primality and factoring numbers is very hard when they are big. So here are some examples. 2 squared minus 1 is 3. 2 cubed minus 1 is 7. 2 to the 5th minus 1 is 31. 2 to the 7th minus 1 is 127. Those are Mercene primes. While 2 to the 11th minus 1 is 2047 is not a Mercene prime, because when you look at this, you can be factored as 23 times 89. So Mercene primes are very important in the study of primes, and there is a thing called the Great Internet Mercene Prime Search, or GIMPS, and it's devoted to a search for new primes. They have a distributed algorithm where you can rent your computer out to them, and you can join this search and you can find a new prime and possibly even win a cash prize. Now, they do go through an intensive verification process, and you might also be just involved in searching for the primes or verifying for the primes. And even the search for Mercene primes has practical applications. And so now, at the time of this writing of these notes, as of 2011, there were 47 Mercene primes were known, and 16 have been found since they're the largest one. As of 2011 was this number, 2 to the 43,112,609 minus 1. And this is a number with nearly 13 million decimal digits. And this was shown to be prime in 2008. Down here in December 21 of 2018, another larger prime is being found, and this is 2 raised to the 82,589,933 minus 1, and this has over 24, almost 25 million digits. And this was a computer volunteered by this fellow in Florida, made this find on December the 7th. And this new prime number is the largest one that we have. And if you were to write this in terms of digits, it would be 1.5 million digits, which is larger than the previous record number. So this is a serious and ongoing game. Now, the previous theorem tells us there are an infinite number of primes, but how many primes are less than a positive number x? And this has interested great mathematicians over the years, and people produced tables and studied them. This is a very complicated theorem, but the proof of this theorem also is beyond the scope of this book, but we can certainly quote it. So the prime number theorem states that the ratio of the number of primes not exceeding x and x over ln x, where that's the natural logarithm of x, approaches 1 as x grows without bound. So what this means is that the primes are theta when we talk about order of growth of, the number of primes less than x is of the order of, or I guess we called it theta of, x over ln x. Now we can use this to estimate the odds that a randomly chosen number is prime. The prime number theorem tells us that the number of primes not exceeding x is approximated by x over ln x. So the odds are going to be 1 over ln n. So you see these get further and further apart. And we'd like an estimate of how many integers with a particular number of digits are needed to select before we encounter a prime. And so what we can say is that you would have to take ln this. And so, for example, the odds that an integer near 10 to 1000 are prime is approximately 1 out of 2000. And the more we go up in numbers, the more and more scarce they get. And so using trial division gave procedures for small numbers, but these numbers are too big to approach in that way. However, and when we get to encryption, you'll see that although multiplying is easy, factoring is hard. And so that is actually what we use is we build upon this because there's no polynomial time algorithm for factoring integers is known. So the challenge of factoring large numbers interests many people. And there's a huge effort in the internet to factor large numbers, especially those of the special form k to the n plus or minus 1. These are called Cunningham numbers, and there's a whole field of study here. We also study primes and arithmetic progressions. Every odd number is of one of two progressions. Either it is 4k plus 1 or 4k plus 3. Because we know that there are infinitely many primes, we can ask if there are infinitely many primes in both of these progressions. These primes are in the first progression, and these other primes are in the second progression. Evidence hints that there's maybe infinitely many primes in both progressions. But what about other arithmetic progressions, where no integer greater than 1 divides both a and b? These are the form ak plus b. Do they contain infinitely many primes? And the answer is yes, they do. His proof is well beyond the scope. So we have explained that every arithmetic progression ak plus b, where a and b have no common factor greater than 1, contain infinitely many primes. But are there long arithmetic progressions made up just of primes? For example, some explorations show that 5, 11, 17, 23, and 29 is an arithmetic progression of 5 primes, and this one has 10 primes. So in 1930, a famous mathematician, Paul Erdős, conjectured that for every positive integer n greater than 2, there is a progression of length n made entirely of primes. And this was proven in 2006. Their proof was an amazing thing, and in fact, but it also is a non-constructive proof. It doesn't tell how to find them, and it used powerful methods from many areas of mathematics. Now, there are many conjectures and open problems about prime. Some people say, well, is it possible to have a function such that f of n is n for all positive integers? And one thing that some people have talked about is f of n equal n squared minus n plus 41, because this polynomial has an interesting property that f of n is prime for all positive integers n not exceeding 40. But what happens is that this is not doesn't work for everything, because f of 41 is equal to 41 squared, meaning it doesn't give you that. And in fact, it can be shown that every polynomial f of n with integer coefficients that exist in integer y such that f of y is composite. So what we do know is at least there's no polynomial. There may be a function somewhere, but it's not a polynomial. And some more famous problems that exist, Goldbox conjecture. And Goldbox conjecture is that every even integer n greater than 2 is a sum of 2 primes. So for example, 4 is 2 plus 2, 6 is 3 plus 3, 8 is 5 plus 3, 10 is 7 plus 3. Now, Goldbox conjecture has been verified for numbers up to 1 million prior to computers, And with computers, it checked it up to some very large numbers, 1.6 times 10 to the 18th. But there is no proof. And some people have made some progress of this, and this talks about the results. Among the results is that every integer greater than 2 is the sum of at most 6 primes, and that every sufficiently large positive integer is the sum of a prime and a number that's either prime or the product of 2 primes. So maybe there will be progress, but as of this lecture, Goldbox conjecture is not solved. Another conjecture is, are there infinitely many primes of the form n squared plus 1? The best result currently known is that there are infinitely many positive integers n such that n squared plus 1 is prime, or n squared plus 1 is the product of at most 2 primes. And there is also a twin prime conjecture. Twin primes are pairs of primes that differ by 2, such as 3, 5, 5 and 7, 11 and 13, 17 and 19, and 4,967 and 4969. The prime twin conjecture asserts that there are infinitely many twin primes. The strongest result proved concerning twin primes is there are infinitely many pairs, p and p plus 2, where p is prime and p plus 2 is prime, or p plus 2 is the product of 2 primes. And the world record for twin primes, as of the writing of this book, are the numbers this number times 2 to the 333, 333 plus or minus 1. And this has 100,355 decimal digits. So this is the kind of things people study in number theory, and they're dealing with large primes. And we're going to see that large primes are very important in encryption. But for now, more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of each other. We're all in this together. May God bless you all.